Thank you for your introduction. So that's all. Okay. So this paper deals with the distribution of stresses in welded joint specimens, which were made with multiple combinations of defects. It is a part of a very extensive research, which was included in the PhD thesis of that long-haired gentleman in the corner. And among our many presentations on the subject, a couple of years ago, Professor Filippo Berto observed, based on our results, that we should probably focus on the stress values not only along the main axis of welded joint specimens, because the defects would cause geometric irregularities and asymmetry, and some of our specimens would deform in very unusual ways, which would also lead to considerable stresses along the perpendicular axis. So we finally got around to perform this stress analysis, because we also believed it could explain how certain defects were critical in some of the cases, in some combinations, but in other combinations, the different type of welded joint defects would take over. Now, this is one of our older results, the two-dimensional version. This was the misaligned specimen. You can clearly see all the defects here, in the geometry. And here we only, in this case, we only have the results for the vertical axis. And you can see that the magnitudes of the stresses are almost 240 megapascals, which is definitely not what you get when you do the tensile tests on specimens without defects. So for this purpose, we decided to, this time, develop 3D models based on the previous versions in terms of geometry, but we'll just add the thickness in Abacus software version 6.17. The choice for the 3D models was motivated by two things. First, we wanted to see if we would get any differences, but honestly, we didn't even expect that would happen because of the plane strain state and everything. And the real reason was because we intend in the future to work with 3D specimens to simulate fatigue. And we took the opportunity to prepare these models in advance and to get at least a little bit different pictures, so to not confuse people, because we really have a lot of results on this topic. The model geometry, like you saw in the previous slide, was measured directly from the specimens in detail with every dimension of every defect and misalignment, and even the slopes of the plates, which in some cases bent during the welding, were taken into account. We had initially, in our previous researches, we had 4 groups of defects, but this time we decided only to focus on the 2 critical ones, which had 2 millimeters vertical misalignment, because here we expected that these stresses outside of the main axis would be much greater. And here you can see these 2 models in 3 dimensions with the finite element mesh, which of course was refined here in the weld metal area, the critical parts, and also in the immediate vicinity. These parts here with the finer mesh represent the heat affected zone, which had its mechanical properties determined by an iterative method, which you can find in our other papers. So I don't want to really go into detail about that now. Of course, it took us several iterations to get the right site to ensure the convergence of our models. And here we have the boundary conditions and the loads, which of course correspond to the experiment. The one end of the model was fixed and the other was subjected to a pressure in this case, which corresponds to the force which in the experiment would cause the model to start entering plasticity. And here we have some of the results this is for the 3rd group model, or the first case with the misalignment, which also had the undercut and the excessive weld metal. And here, this is the equivalent von Mises stresses, which, like we said, corresponded to the point at which the model starts entering plasticity. These were the critical areas here, because this is where the heat affected zone with this property would enter plasticity, and we will get something like 1% plastic strain, and decided to stop there. But as you can see, when you look at the vertical stresses along this axis, they have some very high values. This is 183 megapascals, and that's really definitely affecting the overall equivalent stress values. you can also see that some of these are actually negative and that they even form compressive stresses, which I will explain in a little more details soon. This is the fourth group of the specimen, which also had incomplete root penetration, among other defects. And it was proven previously to be the most critical of all of the defect combinations that were considered. So here you can also see the equivalent mesostresses. And here you can see that the vertical stresses play an even bigger role because now their values are even above 300 megapascal, and also, but some can go as low as minus 94, as you can see in some of these areas here. Of course, the critical values were always where we would expect most of them to be, here at the fusion lines or at sudden transitions in the geometry. So first, we confirm what we pretty much already knew, that the 3D and 2D models there won't be any variations along the, just a sec, that there won't be any variations along the third axis, but I already explained why we decided to go with it anyway, and that the stresses outside of the main axis were much higher than you would usually expect compared to specimens that wouldn't have any defects. In the first case, they were 43.2% of the maximum equivalent stress, 183 if I remember correctly. And the second case, they were 67.5. That's over 2/3 of the maximum stresses that were obtained for its model. But something that is probably even more interesting than these magnitudes alone was how it affected the stress distribution, because of what I was mentioning previously, specifically referring to these negative values and compressive stresses that, for example, occurred here or here, and they would effectively decrease, in some cases, the equivalent stresses. So if we had the same model like this, but without the misalignment, so the plates were perfectly horizontal, then this undercut would be the critical location where eventually a crack would initiate and it would fail, like it happened in the experiments. But when you introduce the misalignment, then during the experiment, the specimen begins to bend in irregular ways, so it goes like this, and eventually, in some cases, it would produce compressive stresses here, which would decrease the overall stress in this area and effectively eliminate the undercut as the critical defect. Instead, the tensile stresses would concentrate around the root, and this is where the cracks would initiate and it would fail. Also, what's interesting is that, of course, because of this decrease, the values, if we observe along the axis of the welded joint specimen, we would get some very high values, and in certain cases, they were almost around 700 megapascals, which by far exceeds both the yield stress and the tensile strength of any materials. But this kind of deformation actually managed to negate them and lower them to the level of 460 megapascals, which we obtained in the case when plasticity initiates. So in our case, these stresses have a very significant influence on the overall integrity and the fracture behavior of the welded joint. So once again, let's summarize this quickly. The research presented a 3D numerical analysis of the effects of geometric irregularities and asymmetry on stress distribution due to stresses outside of the main axis, which had very significant values between like almost half and 2/3 of the actual equivalent stress, and that the use of 3D models in here wasn't really necessary, but it will be very useful for us in the future. Now, we also plan to continue this research in more details and to try to further combine it with a lot of experimental results we have, like from digital image correlation, where we can make even more detailed comparisons between the stress distribution. And that would be it for now. So thank you for your attention.